Welcome students to your video on using graphs to relate two variables. We're going to be looking at a selection of various graphs, and we're going to be looking at how we can talk about what the variables are that are related, how they are changing in relation to one another. We're going to be looking at kind of practical circumstances. We're not really going to be seeing a whole lot of numbers on these graphs, if any at all. Looking more at a relationship. In the background, you hear some Phoenix. I like Phoenix. They're French. I haven't downloaded the new album yet. Haven't been able to afford it for a while here, but that's something I plan on purchasing next time I have spare money. This album is called Phoenix, and I am going to figure out how to put my little disclaimer on YouTube so, I don't get arrested in the middle of class one day for plagiarizing someone else's music. I don't think it's called plagiarizing. Anyway, copyright infringement. That's what it is. Anyway, let's get started. Okay. So they give you three graphs, and these three graphs below are relating the height of water to the volume of the water in each of these three containers that you see over here on the right-hand side. You have a little cylinder, a tall, skinny cylinder, and then this one is a cylinder with kind of a cone-shaped top. And they want to know which graph goes with which container. Take a moment to sketch the graphs and sketch the little containers and think about what's going on. Pause it if you need to. Okay, so what we're looking at here is we're looking at how the volume relates to the height. Okay, so if I look, for example, at this container right here, let me actually draw a little bit. So that container is a cylinder, and it's kind of short and squat. So the height of the water is not going to go up very quickly. It's not going to increase that fast, and it doesn't have that far to go. But the volume is going to increase pretty quickly as the height increases because it's such a wide container. It has, it's kind of squat, kind of wide. So which graph do you think that is if we label them 1, 2, and 3? Why, yes, that would be graph number 2. Graph number 2 for that short cylinder. So graph number 2 is the one that tells us, that shows us that the volume would be increasing slowly, and that the height doesn't actually go that high at all. You see, it stops at a pretty low level right about there. Good. Okay, let's look at the next one. Okay. Next one, tall, skinny cylinder. You've probably already figured out that that's going to be number 3 because the height is going to be consistent. Same thing with the second one. The height is going to increase consistently as you pour the water in, and we're pretending that we can pour really steadily and evenly. So as you pour the water in, the height is just going to go straight up, right there, and the volume is going to increase at the same time. And then, of course, by process of elimination, also because of the shape of the graph, this cylinder with the cone-shaped top here, this one, so it looks like a flashlight that's upside down, right? This one is going to, the volume and the height will increase steadily, and then suddenly it's going to veer off. You see that right here? Because suddenly the height is not going to go up as fast as the volume increases, because the volume can increase faster since the radius gets bigger as you go up here, or the diameter, either one. Okay, so it's an interesting question, a way to think about what we're seeing on the graphs and what we're seeing for these cylinders. So let's keep going with another example. Okay, analyzing a graph. This graph shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. Now, I know that you have an answer already here, but let's kind of go through it together. So the variables here are time. Oh, that didn't work. Hold on. Let's try that again here. Time, there we go, and volume. Okay? And they tell us, so the volume increases as you blow up the balloon. So as time increases, volume increases. And it's not constant because you can't necessarily blow up the balloon consistently. Okay, you have to take breaths. You're not superhuman. You're gonna have to take little breaths. Where are the breaths happening? Oh yeah, right there, and there, and there, and then eventually you've gotten too full, and boom, the volume goes straight down to 0 immediately when it pops. Okay, and it says in the middle of the fourth blow. So each diagonal. So this is 1, 2, 3. This is the fourth time we're blowing up the balloon, and that's when it popped. So analyzing the graph is a question of looking at the circumstance, thinking about what they're actually talking about in the circumstance, and trying to relate what is actually happening in reality to what you see on the graph, the relationship of the two variables. Okay, moving on now to a different example. Okay, sketching a graph from an actual situation. And I know we skipped over numbers a little. This is problem 3. We kind of skipped problem 2. That was recognizing a graph from a table. I think we already know how to do that, so I skipped it. Okay, but this one, so let's read it. A model rocket rises quickly, then slows to a stop as its fuel burns out. It begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. What sketch of a graph could represent the height of the rocket during its flight? Label each section. So someone has completed this one for us, and you see you have a long x-axis, a little short y-axis, time on the x, height on the y. That you're always going to see time on the x because time passes in a linear fashion. Time passes from beginning to end. So it's a good way to show the passage of time to put it on the horizontal axis. Okay? And so they drew the curve, so it's rising quickly. So rising quickly. Stops as it's burning out of fuel, falls quickly, and then the parachute opens and then it falls slowly. And so at each point you can see what's happening. It stops rising here. Okay? It doesn't go straight, jerk to a stop, and then straight back down again. It has a curved path. A projectile always follows a curved path. Had it not had a parachute, it would have just done like this. Okay? Had it not had a parachute, that would have been what we saw. Okay, but it's got a parachute, so it changes it a little. So that's not too hard a situation. Let's try out an example or two of our own. Okay, so here's the circumstance we're going to draw a graph for. Suppose you start to swing yourself on a playground swing. You move back and forth and swing higher in the air. Then you slowly swing to a stop. What sketch of a graph could represent how your height from the ground might change over time? Label each section. Okay, so we need a y-axis and an x-axis. I'm going to make it nice and long so I can make sure I understand what this is going to look like. We're going to have time there and height on the y-axis. Now, what would be logical units for the time and the height? Just like the other ones, seconds for time and maybe feet for height this time, because we don't have kilometers or miles or anything like that, because you're not going to go up kilometers in the air. You're cool, but you're not that cool, folks. That's not how a swing works, and you know it. Okay. You're also not going to start on the ground, so we're not going to start down here at the origin, because you're not sitting on the ground. You're sitting in a swing. So as you start swinging, your height from the ground, you're sitting on the swing, is in the swing. And then as you start swinging, every time you pump your legs, you're going up higher. And it's taking longer to come back down. All right, so once you get to the point where you decided to stop, because it tells us here, then you slowly swing to a stop. We're going to start having the same path, but it's going to come back down until you've stopped. Okay? And if I was actually, say, like a photographer, imagine a photographer standing in front of you, snapping a picture every quarter second, using one of those cool DSLR, those cameras that can take like 400 pictures in a second or something ridiculous like that. I'm sure I got the number wrong. Just bear with me. Imagine they're taking those pictures. They're watching you from the side. Your height is going up and then down and then up and then down as you swing back and forth. And then you slowly swing to a stop. Now, let's look at B. So we'll use a different color for B. I'll use this nice green color here. Okay, so if you jumped from the swing instead of slowly swinging to a stop, how would the graph in part A be different? So say that I'm swinging and I'm swinging and I'm swinging. Okay, and I decide at the height of this jump right here that I'm going to jump off. So what do you think is going to happen? Well, do you think you're going to go up higher? Well, yeah, if you jump off at the height of the graph, you're going to go up higher. And what's going to happen to your height above the ground? It's going to go up a little bit, and then you're going to come down. And you're not going to go straight down in a second. You're going to come down. And I guess that makes sense to me. I don't see how it'd be any different, right? So at that point, now I'm on the ground. So that would be for B, would be our nice green color there. Kind of green. And hopefully when you jumped off the swing, you didn't break a limb. Okay, guys, one last slide. Just a little thing to wrap it all up. So I want you to go ahead and try 1, 2, 3, and 4. Remember to write down at least the basic idea of each question, or just go ahead and copy the question. That way you can make sure that you have everything together. This is in your textbook. For those of you interested in actually using the real paper textbook to follow along, just in case there's anything there to help you, it's on page 237. All right, pause it and try these. Pause it and try these, and then start it up again, and I'll be going over them. Okay, number 1, what are the variables in the graph at the right? Use the graph to describe how the variables are related. All right, so the variables in that graph are car weight and fuel used. And this makes sense. We actually talked about this in the classes that got to rate times time equals distance problems. You're kind of shocked to see that an aircraft carrier only goes at about 6 kilometers an hour. Well, it's kind of heavy, so it takes a lot of energy even to have it go 6 kilometers an hour. As the car's weight increases, okay, so as car weight goes up, as car weight increases, so does the amount of fuel used. And that's about it. Good, all right, 2. Relationship between the time and the temperature. Okay, so look at the time, number of hours, afternoon, so 1 o'clock, 3 o'clock, 5 o'clock, 7 o'clock. You watch the temperature goes up a little and then starts coming back down. All right, so the temperature rose to a high of 62, which we don't know that was the high of the day, but for this time period it was the high, then fell as it got late. Okay, and being the time of year where it's going to be dark at 4 p.m. soon, this is something we're pretty well used to, huh? Good. Excellent. Now I'm going to go ahead and write on the actual problem for the next one. So I'm going to change my writing color to a dark one just so it's a little easier to see. Match one of the labeled segments in the graph below with each of the following verbal descriptions: rising slowly, constant, and falling quickly. So where would you say this is rising slowly? Well, I definitely would say it's not here because that's falling. It's not here because that's rising quickly. Good. All right, and it's not here because that's staying the same. So rising slowly, I think, is B. So rising slowly, I think, is B. Let me get my writing tool. Rising slowly is B. That didn't work. Hold on. Good enough. Okay. Where is it constant? So constant means it's staying the same. So where is that staying the same? Where is that staying the same? It's staying the same or constant at C. Well, that's convenient. C for constant. Okay, that's gotten very messy. Let's just fix this, shall we? Much better. Now, which one is falling quickly? Very quickly indeed, because it's going almost straight vertically down, and that would be D, falling quickly. Okay. What could be a real-world situation represented by the graph sketched above? So that's the graph in number 3. Okay, so that's number 4. What could that actually be? Well, that could be my speed on the way to work. My speed on the way to work. So we could have, this could be time down here on the X, and this could be speed. And Miss LeCompte is late, so starting off in A, she's going kind of fast. All right, and then in B, she's gotten to the point where she can't increase her speed too much more. And then C, she's on the highway and staying at a constant speed. D would be getting off the highway, so your speed decreases very quickly. And then maybe E would be coming down Mercury Boulevard from the highway exit so that I can slowly decrease my speed till I get to school. So that's a great example, and I look forward to hearing your examples in class. I'm sure they'll be unique and interesting, just like all of you. All right, guys. Thanks for watching. I'll see you in class.